So, a certain current, this is a continuation of video 1. We've explained Faraday's laws of electrolysis and we derive a lot of formulas from there. And we are going to apply it here in the, subsequent examples. So, a certain current liberates 0.50, 0.504 grams of hydrogen in 2 hours. How many grams of copper can can be liberated by the same time in aqueous copper sulfate solution? I should have it can be here. Now we have the mass of hydrogen to be this, and we have our time in this, and we are to relate hydrogen to copper. So you could see that this is typically a typical application of the second law of Faraday's electrolysis, which states that if we have the amounts of a substance A and its equivalent weight, provided substance A and substance B are connected in series and the same current is passing through them, this relation should be true for them. So this is the mass and this is the equivalent weight of A. This is also the mass of B and its equivalent weights. So now we have mass of hydrogen. Let's say to be mass of hydrogen is given, right? And so this is our formula. We know our mass for hydrogen to be 0.504 grams, right? And then, but we don't know the mass for copper. And before we be able to calculate for the mass of copper, we should know the equivalent weight of, hydrogen. Let's say if A is hydrogen and B is copper, hydrogen, and we should also know the equivalent weight of copper. What is the molar mass of copper? We know the molar mass of copper to be 63.5. And for equivalent weight equal molar mass of the substance over its n factor. And we know molar mass for copper. And what is the n factor for copper in copper sulfate? We just break copper sulfate into its ions like ionic form. So we are going to get the charge on the cation is the n factor. As far as this substance is a salt, so the charge on the cation, not the anion, is the n factor. So we are going to get our n factor to be 2. So molar mass of copper 63.5. So 63.5 over 2, and this is going to give us 31.75 grams. That is the equivalent weight for copper. So you also have to look for the equivalent weight of hydrogen before we can use this formula to calculate for the mass of copper. So what's the molar mass for hydrogen? You need to know the molar mass for hydrogen and its n factor, so equivalent weight for hydrogen, let's say hydrogen is equal to molar mass of hydrogen, which is just simply as 1 over its n factor. Hydrogen is going to give us 1, so we have 1 gram. So now we can make W the subject as the mass of copper. Let's say, let me use this, hydrogen over E hydrogen should be equal to W copper over E copper. So with this and making W as a subject, we are going to get our W, which is mass of copper, to be equivalent weight of copper. We know the weight of hydrogen, which was given as 0.504. So 0.504 grams all over the equivalent weight for hydrogen. We calculated it to be 1 gram. So 1 multiplied by the equivalent weight for copper, which is 31.75 grams. And this is going to give us, this is going to give us 16.002 grams. What current strength in ampere will be required to liberate 10 grams of iodine from potassium iodide solution in 1 hour? Now we are looking at current. So what have you been given so far? You've been given mass of iodine. So weight of iodine, go 10 grams. And then our time also given to be 1 hour. This will give us 60 by 60, giving us 3600 seconds. For our current, we don't know. That's what we are actually looking for. So what equation are we going to use? Let's use this. Mate MEF. So now we know our T, we don't know our I. That is what we are looking for. We know our M, molar mass for iodine. We can just look for molar mass of iodine, which will give us 127 gram per mole. And our N factor for iodine in potassium iodide. We know the chemical formula for potassium iodide is simply Ki. And if we break this into ions, we are going to get K plus and A minus, I minus. So the N factor here is 1. So we know our N to be 1. So now let's start calculating by making I the subject, which is what we are looking for. By making I the subject, we are going to get I equal WNF over MT. So we know our W to be 10 grams. So 10 grams by N to be 1 multiplied by Faraday's constant 96500, all divided by molar mass for iodine is 127 grams per mole, and our time in seconds is 3600 seconds. And this is going to give us 2.11 ampere. Let's solve 2 more examples, including this. What mass of ion can be produced when 45.2 ampere is passed through a molten iron trichloride cell for 1.5 hours? So we have our current I to be 45.2 ampere, and we also have our time T to be 1.5 hours. So 1.5 hours, we know 1 hour gives us 60 seconds. So half an hour is going to give us 1 hour gives us 60 minutes, and half an hour is going to give us 30 minutes. So you just multiply. So 60 plus 3 is going to give us 90 by 60, and this is going to give our time to give us in seconds to be 5400 5400 seconds. So now, what formula are we going to use? We are going to look at the mass of ion So it's better we use this formula from the first law of Faraday's electrolysis. Meet NEF. Now we can easily tell our F. We know our T, we know our I, and then molar mass. And here we are looking at ion. Molar mass for ion is going to give us 56 gram per mole. I prefer always breaking the sample given to us like iron trichloride into 8 component ions. So Fe trichloride, when I break it into 8 ions form, I'm going to get Fe3 plus Cl minus. So after this, our N is simply the charge on the cation, which is 3. So in this case, our N equal 3. Then now we can go ahead and calculate for the mass of ion produced. The mass of ion produced. So let's go. We get our W to be equal to molar mass of copper, which is 56 grams per mole. This is 56 by current, which is 45.2 ampere, and by time, which is 5.5400 seconds, all divided by n factor, which is 3 by Faraday's constant, 500. This is going to give us 47.21 grams. So this is the mass of ion that can be produced when 45.2 ampere current is passed through a molten FeCl3 cell for 1.5 hours. What volume of oxygen will be deposited at the anode when current of 2 ampere, when current of, let's say, 3 ampere is passed through a dilute MgSO4 solution for 45 minutes and 30 seconds? I'm giving the molar gas volume to be 24 liters at standard temperature and pressure. And our Faraday's constant is also given to us. 1 Faraday equal 96500. So now, this is an acidified solution problem. How do we solve this problem? For acidified solution problems, first of all, we have to identify our ions in the solution. And we have MgSO4 in the solution. MgSO4. So the ions, among the ions that we are going to get in the solutions are Mg2 plus, the composition of this compound, SO4 2 minus. Because MgSO4 is in solution, we also have H plus ions and OH minus ions in the solution. So, because the anode is positive, both OH minus and also for 2 minus will be directed towards the anode, but the one that is preferable is OH ions. This is the principle known as the preferential discharge of ions. So OH minus is the preferred ion that will be deposited at the anode. So OH minus aqueous will be oxidized to give us oxygen gas, water and oxygen gas plus electron. That is to balance the equation, charges. So at the anode, OH, that is OH minus that is moved to the anode will now oxidize back into water and then give us oxygen gas. And this oxygen gas is going to be deposited at the anode in the form of bubbles. So we can go ahead and balance this equation by, we can bring 2 here and then 4 here. Then we can also add 4 here. Let me write everything again. So you have 4 OH minus aqueous giving us 2 H2O plus O2 gas plus 4 moles of electrons. So our N factor here for what is causing the liberation of hydrogen oxygen gas is 4. So our N here equal 4. Now we know N value, the value for N, and we know our current to be 3 ampere, and we know our time to be 45 minutes 30 seconds. Converting this to seconds is going to give us 2730 seconds. 2730 seconds. And then our Faraday's constant, we also know it. But what formula are we going to use exactly to calculate the volume of oxygen that will be deposited at the anode? Sorry. From Faraday's first law, we know that mass deposited will give us meter Nef. In terms of volume, we can also write this in terms of volume by saying that our volume of gas evaluated, is going to give us the molar gas volume at standard temperature and pressure IT. We just replace our molar mass by molar gas volume over NF. So now we can do substitution. We know our N factor, our Faraday's, and then our molar gas volume was giving us to be 24 liters. So now let's proceed. So we are going to get 24 liters by our current, which is 3 ampere, by our time, which is 27. I'm going to write this here. So 2730 seconds, all on our N factor, which we know to be 2, by Faraday's constant, 96500 kilo. And this is going to give us 0.5092 liters of oxygen gas. So that's our final answer. Thanks for watching.